Well, yeah, I'll start with the ancient Greece, obviously, then the beginning of 20th century and the basic discoveries which led to establishing the nuclear physics as we know it, more or less today. And then key concepts which led to the development of nuclear weapons eventually, because that's, I think, one of the main interests of well, the science for peace movements and this particular lecture session. And that would be chain reaction and discovery of nuclear fission. And I'll say just a few words about the construction of the bomb, the Manhattan Project, because this is really a key key aspect. However, I know there will be other lectures in the future which will cover that in more detail, so we'll not spend too much time there. Okay, so, well, people had concepts of atoms or some indivisible, uncuttable constituents of matter already ages ago, and you must have heard about the Democritus, who was essentially the first one who had that idea. And of course, they have nothing to do with atoms as we know them today, or that broad philosophical concept doesn't relate too deeply to elementary particles as we know them today. However, this notion of some little bricks which, when put together, constitute matter was around for a while. Looks like people were almost intuitively coming up with that thought. Also independently in India, more or less at about the same time, similar ideas showed up. It kind of goes through all those, also some Buddhist texts, curiously enough. So, well, it's been out there for a while. So, apart from that idea being present, nothing really happened for until year 1800, when John Dalton came up with the first idea, first hypothesis based on actual evidence, and that evidence was a simple observation that basic elements. By that time, people learned how to separate elements, such as sulfur, carbon, some metals, just to give you an example. And that basic observation was that these elements react in ratios of small whole numbers. For instance, for one part of sulfur would react with 2 parts of oxygen, or similar combinations to that one. And early chemistry really emerged from that observation, trying to write down chemical formulas and follow the chemical reactions was possible even before the existence of atoms was proved. That was just an empirical fact that people were relying on. This is a page from Dalton's book with his imagination or his concept of atoms and images of chemical particles that were created from various elements. Just the very first idea on how something like that could be happening. And yeah, it doesn't really work like that exactly as on these pictures, but it's close enough to the reality. As far as atoms are concerned, nothing really happened for the next 100 years. The actual experimental evidence of their existence happened around, well, the beginning of 20th century. In 1905, Brownian motion was explained by the atomic theory mathematically, which was the first solid proof for the existence of atoms. What is Brownian motion? Imagine you put a little grain of pollen in a glass of water and try to follow its movement. So it's not easy. People do that under a microscope. There was a physicist or chemist, Brown, who studied that. And trying to draw the trajectory of that grain of pollen would give you a very complicated random shape. Essentially, this little particle would bounce around in random direction. And it wasn't immediately clear why. People then thought, okay, this is because atoms of liquid, of water, or particles of water are kicking that grain of pollen from random directions, and this is why it ends up bouncing around in this random pattern. And it became possible eventually to really model that mathematically based on that very simple assumption, and then compare that with reality. This allowed to actually evaluate mass and sizes of particles of water. So that was the major experimental proof. As you see, 100 years passed, and yeah, that's the major thing that happened. The 19th century physics was extremely successful up to that point of atomic and subatomic scale. What happened, well, in 19th century and earlier was developing the Newtonian mechanics, the Maxwell's theory of electromagnetism, thermodynamics. They were all extremely successful on a macro scale, allowed to rapidly develop industry, understand how things work pretty much, construct machines better, more efficient. That really drove the rapid progress, the growth of civilization in that time. People were so impressed with that they actually thought, well, it's been so great that we understand everything. We have that mechanistic concept of reality and universe, and there's really not much missing, or maybe nothing missing. There is a famous quote which is often attributed to Lord Kelvin. It's actually not that clear who really said that, but well, anyways, he allegedly remarked that the future truths of physical science are to be looked for in the 6th place of decimals, so there's really nothing new to discover. One of the very few open questions, just curiosity that people were starting to investigate at that time, was X-rays. So in particular about X-rays, Lord Kelvin's thought was that it will prove to be a hoax for sure, and there is nothing behind it. So I really just wanted to emphasize the state of mind of end of 19th century physicists. After a long, stable progress, there was certainly some stagnation. There was nothing new being discovered, just perfecting the already existing knowledge and understanding of physics. So in a way, it's a disappointing view, and there certainly were a lot of people who were really looking forward to new challenges and new mysteries to solve. And well, there were a few. I'll start with J.J. Thomson and cathode rays. So coming back to that thought about atoms, that was the first time when people realized that atoms, the chemical atoms, might actually be divisible, might not be the most fundamental particles of matter. And it all started with that simple device, which you can see here on that barely visible image. What it is, it's essentially a glass tube with vacuum inside. In 19th century, people learned how to achieve good vacuum, how to use electricity. an obvious thought was to try at some point, okay, what happens if we try to push some electric current through vacuum? So at certain levels of vacuum, if the pressure is low enough, what happens is this kind of fluorescing ray appears. You can see that on the left side of the image. That's a so-called cathode ray. Coming from the cathode to the anode, the other electrode, and there is some greenish fluorescence on the glass appearing on the opposite side. So Thomson studied that very faint beam in the first part of in the left part of the tube. Tried to understand what it is, how it behaves, what affects its behavior and shape. So he quickly discovered that this is a stream of negatively charged particles. Basically, by putting electric field near that tube, he was able to deflect that. He also noticed that magnetic fields bends those rays. So after performing a series of pioneering experiments, he really concluded that, well, there is no other explanation. These are charges of negative electricity carried by particles of matter. This is the first time the idea of electron shows up in science. He actually managed to measure their mass relative to proton mass, although people didn't really have any idea of protons at that time, so relative to hydrogen mass, and found that it's more than 1,000 times lighter. So that was something new. We had these atoms for more than 100 years, more or less established. Now it turns out that they do have something negatively charged inside, which is much, much lighter than the atom itself. And it looks exactly the same regardless of what type of atoms it's coming from. So that triggered a lot of further research and gave Thomson a Nobel Prize. The same device, the Crocus tube, also played a crucial role in the discovery of X-rays. Turns out if the voltage applied between the electrodes in the tube is high enough, in addition to that greenish fluorescence that you saw in the previous pictures, for some unknown reason, photographic plates in the vicinity of that tube darken, even if there is no direct light path, if they are wrapped in black paper or something like that. So many people actually observed that, but the first one who really studied that in more detail was Röntgen. And found that these rays were, they were clearly invisible with naked eye, but that they also could penetrate matter very easily. Which is why the photographic plates wrapped in some materials were still exposed and did show some pictures. So that's one of the first intentional X-ray images ever made. This is Röntgen's wife's hand with a wedding ring. I believe that was around 1895. That was a major breakthrough, although people really regarded that as more of a circus trick, initially at least. It found a lot of applications right away in medicine, medical imaging, for example, and other things. But more importantly for our topic is the fact that it inspired another physicist, a French, Henri Becquerel, to look at uranium minerals with some more attention. So what inspired Becquerel really is is the connection between that greenish fluorescence at the end of the tube and the fact that X-rays do appear to do something to photographic plates. So he tried doing the same with fluorescing minerals containing uranium that he was researching. It's just a simple thought. Those minerals, he thought, well, they expose some fluorescence after they are exposed to light. If you move them to a dark room, they give out a very faint glow. So he thought there might be also X-rays involved. What he did is he put one of these nicely looking stones on a photographic plate, again wrapped in black paper. The next day after developing that, he did see a clear shadow. So that was an interesting discovery, although the interpretation was completely wrong, and he wouldn't have known that it was wrong if he didn't do another test on the next day. Again, he exposed the mineral to sunlight. At least that was his intention. And then, well, the weather in Paris was really bad, so there was not much sun. It was pretty dark. Nevertheless, he decided to try again, and he put that rock on the photographic plate. He developed another plate, and again he saw that shadow, that dark contour. So, to his surprise, he discovered that those minerals would emit something similar to X-rays, regardless of whether they were exposed to sunlight or not, which was a completely different result from what he expected. And they were a little fainter than the radiation seen from the X-ray tubes, so they were dubbed uranium rays initially. And the scientific community, initially at least, pretty much ignored that discovery. It didn't seem to be attractive enough for serious scientists to pick up. And here is where Marie Skłodowska-Curie comes into play. He was certainly a serious scientist. However, well, she was looking for a challenge, for sure. And at that time, for a woman to find a place in science wasn't an easy task. So perhaps that's one of the motivations for her to pick a very risky and challenging research topic. So her hypothesis, which motivated the following research, was the thought that radioactivity, or that effect observed in uranium minerals, is a property of atoms itself. Certain atoms at least. So joined by Pierre Curie, she performed a broad survey of various different minerals, and also discovered similar effect in certain minerals containing thorium, which was a proof of her initial hypothesis. Then it turned out that some uranium ores were more radioactive than the pure uranium itself, which triggered another question. Okay, so perhaps there are some other unknown radioactive elements present in that uranium ore, and they are more radioactive than uranium itself. So that little rock, which looks very unimpressive in the top corner, is so-called pitch blende. It's a mineral mined in Austria in large amounts, which was her target of research for the next few years. So how would one prove or try to isolate those new unknown radioactive elements from something like that? With a lot of labor, she would ground it to really fine powder in mortar, and then try various chemicals known to react in a certain way with all known elements. say, she would use a certain acid on that powder, and with the assumption that it would remove and dissolve certain parts of that mix. A mineral like that contains typically 20, 30 different elements. It's a very complicated mixture. So that chemical separation process was extremely laborious and difficult, but nevertheless successful. In 1898, Marie and Pierre Curie discovered new elements. They called them polonium and radium. This is, by the way, the first time when geopolitics and nuclear physics made a connection. Now, she didn't really isolate them fully in that first test. She only observed the radiation in very small, infinitesimal samples of what she isolated from pitch blende. It took her another 3 years and laborious processing of more than a ton of raw pitch blende ore to get to 0.1 gram of pure radium. They failed to isolate polonium. I will explain a little bit why. Nevertheless, that was a huge success, which gave Marie Curie 2 Nobel Prizes in physics and in chemistry. She's still the only person who got a Nobel Prize in 2 different sciences, and one of the very few who had 2 Nobel Prizes. Radium became a really cool thing, something extremely popular and known, and would make headlines in newspapers on a regular basis. It glows in the dark. It's mysterious. Its health effects were completely unknown at that time. So most of the early researchers working with radioactivity would be completely unprotected, would have no idea about what they were dealing with. So yeah, the death toll was significant, and Marie Curie herself got sick close to the end of her life, and the radiation-induced disease basically killed her eventually. The radioactivity was then discovered and confirmed, and we knew that it was coming from atoms themselves. Another great physicist, Rutherford, picked up that idea at this point, and well, he did very significant research at McGill University at that time. This is when the conclusion was reached that radioactivity, well, Marie Curie knew that there is some radiation which comes out of elements, but there was no idea about what that radiation really was caused by, what would trigger it, what it meant for the atom to emit a ray like that. Rutherford, by studying radium and its radioactivity, found that each radioactive decay is actually equivalent to a transmutation. It's a change of an atom to an atom of a completely different element connected with the emission of radiation. He classified types of radiation that he observed in different cases, called them alpha, beta, and gamma. Soon he and his colleagues realized that gammas were more or less equivalent with X-rays, and betas were nothing else than electrons. It took a little longer to figure out what alphas were, but we'll come back to that. So by studying radium and a chain of elements produced in subsequent decays of its radioactive daughters, he found characteristic lifetimes of all of them, and also made the first estimates of the energy released in a nuclear decay, or in particular in alpha emission. So already at this time, 1903, first ideas appeared about possibility of releasing or maybe even harnessing that energy. They were more expressed as jokes. Nobody would take that seriously, but well, a few famous quotes are listed here. Yeah, conceivable that a wave of atomic disintegration might be started from matter, which would indeed make this old world vanish in smoke. That's Rutherford's quotation. There was a lot of confusion around radioactivity still. People didn't know exactly how these new products of radium decay really fitted into the periodic table of elements. It took a few years and a lot of experiments for people to find out that, well, they really, well, with the exception of radioactive gas radon, which happens to be the first one after radium, they were all known elements from the periodic table, except, well, most of them were, some were new, except they had a property which made them radioactive. Later people realized that various numbers of neutrons in a particular nucleus could make it unstable and radioactive. But that's sort of looking ahead into the future at this point. About radon, important thing to know is that it's a gas. Well, most of you must have heard of that. The way scientists actually realized that decay was connected with transmutation was the fact that once there was radium in a laboratory, eventually radioactivity would be seen all over the place. It would mysteriously migrate from one place to the lab to pretty much everywhere. And the reason is really radon, because it decays itself after a couple of days and deposits its own radioactive decay daughters wherever it gets. So that triggered that and a few other results triggered that conclusion of Rutherford and his colleagues. Some decays are governed by the weak force, that's beta decays. For alphas, it's more complicated. It's an interplay of strong and weak. We'll get to that. So I mentioned about the applications that radioactivity immediately found. First of them was phosphorescing dials for submarines or watches or clocks, something that would emit light even without exposing it to sunlight first. And that's the first large group of victims of radiation. It's a famous example of these women working on painting dials with radium saturated paint, and they would occasionally lick the brush of the tip of the brush to make it sharper, so that whatever they painted on dials would be better. And obviously the death toll in that group of workers was enormous after a number of years. So it took a few decades, I would say, for people to really realize what the consequences were. Initially, people were pretty careless, particularly around X-rays, because it was exciting to look through people's bodies using X-rays, and it was considered generally safe in doses which today would be not, that's for sure. Nevertheless, especially in the First World War, X-rays saved many lives. Marie Curie herself equipped a few dozens of portable X-ray machines which were available in trucks, and trained a number of nurses, and herself participated in attending victims of war. Soon people came up with the idea of also implementing so-called radon seeds in cancerous tissue, and radiation from, in that case, well, radon trapped in those seeds would kill would kill cancer. Of course, again, the adverse effects to healthy tissue would be present there as well at some level. So it took a long time to balance these two properly. And as I said, radioactivity was really cool, and people would start to add radium to literally everything. This is an example of radium saturated toothpaste. As a matter of fact, it was experimentally confirmed that radium would kill bacteria. So obviously, adding it to a toothpaste sounded like a good idea. Chocolate with radium, some hand and face creams, radium water, shoe polish, I believe. That's a more contemporary example. Radium hot springs near Banff. It's the concentration of radon in that water is somewhat larger than considered safe in households, but still consequences for health are negligible. So I wouldn't be afraid of using those. Anyways, that place boomed really around that time when radium was discovered. Moving on. After classification and investigation of different types of radioactivity, Rutherford managed to prove that alpha rays were nothing else than ionized helium atoms. So in some cases, atoms would break into a helium atom, which is one of the smallest ones, and a larger atom. Alphas would usually be ejected with very large velocities, carrying a lot of energy. So Rutherford decided to try to use alphas as a means to investigate and study atoms themselves. He would bombard atoms with alphas coming from some radioactive sources, purposefully prepared for that goal. A big surprise which came up from that in 1913 was the discovery of backscattering of alphas. So after Thomson discovered electrons, people thought, okay, atoms look more or less like a plum pudding. It's some amorphous sphere of positive charge with raisins and plums in it, and those would be electrons. So this is that little cartoon in the top left corner. So with this model in mind, one can calculate what's expected if you bombard an object like that with alphas. They all come through more or less straight without being bent or deflected. However, what Rutherford's colleagues observed was that in some cases, alphas would be reflected back from a thin gold foil that was used as a target. And that was completely inconsistent with this Thomson's model of atom. And Rutherford found the interpretation of that fact by assuming that, well, the entire positive charge in the atom is concentrated in a much, much smaller nucleus in the center of it. So this is the first time the nucleus comes up, really, and its existence is shown. It took another few years, and it's another major discoveries a number of other major discoveries in theoretical physics to really connect that with new developments in quantum mechanics. And thanks for that go to Niels Bohr, another one of Rutherford's students and co-workers. What Bohr did is he took Rutherford's simplistic model of the atom, which assumed that positively charged nucleus and electrons somehow distributed around it, and by assuming that electrons can orbit around the nucleus only at orbits of specific in specific distances, he was able to reproduce a number of real effects from physics, such as spectra of elements observed in spectrographic instruments, and a few other quantum effects which people were scratching their heads about at that time. So this was the beginning of quantum physics, really, and in mid-20s things began to take shape. The final, or more or less standard, formulation of quantum mechanics was reached closer to 1927. And this is important because it's an essential tool for modeling, understanding, predicting all processes which happen on atomic and nuclear scale. Before, people were pretty much guessing what's happening and trying different things, playing and trying to see if there is something unexpected going on, but they didn't really know what to expect. With the atomic theory and quantum-based atomic theory, some predictions could be made for the first time in a consistent framework. So that's a major step. And the last missing piece of nuclear science, before that discovery, people talk that it's really prehistory of nuclear science, not nuclear science itself, was the discovery of neutron. Again, at that time, people knew we had that positively charged nucleus in the center. People already knew about protons and the fact that they are equivalent with ionized hydrogen atom. But, well, what holds all these protons together in the nucleus? Well, that would be some new force, not really known before. Keep in mind that protons are all positively charged, so in principle, if you think about it, there should be a repulsive force between them if you try to stack them together. However, there is a new strong nuclear force involved, which at short distances is stronger than electromagnetic repulsion and basically keeps protons together. And it turned out that there is also another constituent of the atomic nucleus, neutron, which has no charge. And that was really discovered only in 1932 by James Chadwick. So what he did is he bombarded beryllium with alphas. There is a nuclear reaction which happens there, which he didn't know about, which produces free neutrons as a result. Neutrons have no charge, only weakly interact with matter, so they can fly through various materials without leaving much trace. And that makes them different from all types of radiation known before. So by that fact, and excluding the possibility of gammas, alphas, betas, and also by theoretical calculations, he was able to show that it's a new particle and it's electrically neutral. Interestingly enough, two other groups around the world just barely missed that discovery. In particular, Irene Curie and Frédéric Joliot essentially made exactly the same experiment and got the same results, except their interpretation was wrong. And this is what Chadwick picked up and repeated everything with proper interpretation. So perhaps an interesting remark here I could make is at that time the world of physics or nuclear physics was relatively small. I think we are talking about a few dozen people, mostly in Europe. Not so much at that time yet in US and in Canada. And they were all talking, meeting, they had conferences. It was a vibrant field and people felt that discoveries around the corner. They were discovering new things pretty much every couple of years. Each time there was a new discovery, there would be several other groups at that time just millimeters away from making exactly the same discovery. It was moving ahead very rapidly, attracting the best minds because it was so exciting. And also, this is more or less the first time when people started to think about bombs as well. So you remember Rutherford decided to use alphas to bombard atoms and see what happens, use it as a tool to investigate the nuclear structure. After discovery of neutron, people quickly realized that it must be much easier for neutron, which is neutral, to penetrate the nucleus than it is for a positively charged alpha, which would be always repulsed from the nucleus. So they started doing the same with neutrons, bombard different types of atoms. Enrico Fermi in Italy, in particular, did a very careful, systematic study of a number of different elements, and that was a very important step. And in most cases, results were, in some sense, understandable. There would be a new element produced with a slightly higher mass. In some cases, it would decay away immediately to something slightly lighter. The puzzling result, though, was noticed in the case of uranium. There would be some lighter elements in the products after the reaction. It wasn't clear whether perhaps there was a new element formed which would then decay, or whether the target was contaminated in some way. He did publish, in his mind, a discovery of a new transuranic element, thinking that whatever happened, most likely it is a new element which is there in the target, essentially uranium with an additional neutron. But well, another woman at that time in chemistry, Ms. Nodak, questioned his results, and her article was again ignored by the community because people didn't think a chemist, she was a chemist, might have something interesting to say about nuclear physics. She turned out to be right, and what happened is really not production of new element in that reaction, but splitting uranium atom into two almost equal parts, which releases a very significant amount of energy. So in 1938, German physicists Otto Hahn and Fritz Strassmann really observed that unambiguously, and it didn't take too long for Lise Meitner and Otto Frisch to explain that process theoretically. So keep in mind, we are 1 year before the Second World War. People are just learning now that uranium atoms can be split, which releases huge amounts of energy. In the 30s, all scientists of Jewish origin, or with any Jewish members of family or any Jewish roots, had to leave Europe: Germany, Austria, Italy, then Czech Republic, well, whatever was Czech Republic at that time, because of the advances of fascism and Nazism. And all these people went to well, initially UK, France, when the war broke up, the majority of them ended up in the US, and these are the people who really built the bomb. That's something important to keep in mind. Lise Meitner, in particular, who was the leading German physicist, at the time of making that discovery, was already in exile in Sweden, I believe, and was in close contact by mail with Hahn and Strassmann. So yeah, the world was already changing very rapidly, and was never going to be the same. About the release of energy, and this is the Meitner's and Frisch's explanation of why there is so much energy in uranium fission. Turns out if you take a very heavy atom, such as uranium, and measure its mass, and then compare it to the mass of two lighter elements, the elements it splits apart into, you will notice that some mass is missing. It's not exactly the same. These two final elements of uranium fission are lighter. So there is some missing mass. And that's exactly where that energy is coming from. Lise Meitner and Otto Frisch compared that difference in mass, known from very precise measurements people learned to do by that time of atomic masses, and found that it perfectly matches Einstein's mass energy equivalence formula, which is a consequence of relativistic symmetries of space and time. So in uranium fission, in detailed understanding of uranium fission, we managed to link quantum mechanics, Einstein's special relativity, and everything that people learned about radioactivity in the preceding 20, 30 years. So it's like a key which really brings it all together. So if you look at that curve, what we have on the axis is the nucleus mass, and on the vertical axis we have that missing mass. So there are two ways of generating energy in nuclear reactions. One of them is fission, because those heavy elements break into something lighter, there's some missing mass, it converts to energy. The other option is fusion. That works on the left side of the chart, taking two light elements and combining them would again produce something which is lighter than just the arithmetical sum of the two initial atoms. So people realize that this is really what fuels the stars. This is what's happening in the sun. That's the only realistic source of energy of the sun. Reactions between hydrogen, helium, and light elements. So Leo Szilard is a physicist of mixed Hungarian Jewish origin, and that's another curious fact. A number of people who were really critical in developing nuclear weapons and driving that field for many years were people exiled from whatever was left from Austro-Hungarian Empire after the First World War. So it's a very serious overrepresentation of that particular geographic group in those key scientific discoveries of 20th century, and people were speculating why. Well, in addition to Leo Szilard, we also had John von Neumann, Edward Teller, constructors of the hydrogen bomb, 3 other big names, 2 Nobel Prize winners. And the speculation that you can run across in the literature is that because of the rapid political changes in Hungary after the First World War, a short period of first right-wing dictatorship, then communist dictatorship, a little bit of terror from both sides, they kind of went through whatever was going to happen with Europe next. And that experience of initially the First World War, then these 2 opposite regimes, in addition to them being of Jewish origin and struggling with the acceptance of the community in some way, or just the incentive to be a little bit better than everyone else just to survive, made them somehow foresee the future much better than others would. So they left Europe early enough to not get in trouble with Nazism. They were the people who contacted Einstein later on and convinced the US government to support the construction and research on the bomb to stop Germans. But coming back to Leo Szilard, so an example of his exceptional fortune-telling skill was he was the first man who came up with the idea of nuclear chain reaction, which is what is really necessary for the nuclear bomb. And that was just after the neutron was discovered. It was years before people knew that fission was real. He was seeing that far ahead. And for a number of years he was performing his own research relatively quietly, although he did try to alarm the authorities a few times. In the UK, he would file patents on the idea of chain reaction that he would ask the UK authorities to keep secret so that Germans would not use that to construct weapons. In 33, he had that first idea in his mind. In 36, he started to talk to UK, to the British Navy, really, to try to start keeping things secret. In 1933, what happened is, after the discovery of neutrons, Rutherford again started to speculate about releasing nuclear energy and commented that it's impossible and it's moonshine, and that really enraged Szilard, who decided otherwise. The question was which elements are possible to split up, and he was trying the wrong ones. At that time, this beautiful plot I showed you earlier wasn't really known very exactly. There was a number of very severe systematic errors in those measurements, so people were not trying the right elements. And he was the one who did the first few mistakes. However, in 1939, he confirmed the possibility of chain reaction with uranium. So what is chain reaction? I didn't really explain that well. Well, imagine a neutron hitting a uranium atom. We have uranium splitting into 2 lighter atoms, but in addition to this, there are 2 new neutrons emitted. And if there is enough uranium around, they split another 2 uranium atoms, and everything appears. In every single generation, you have a factor of 2 more split atoms, and the energy release grows exponentially, and in a few millionths of a second, energy can be released, which is comparable with tens of thousands of TNT, pretty much. All these numbers were worked out just later, but the idea was already there in 1933. Each time, the energy release is exactly in each individual breakup, the released energy is exactly the same, and it comes from that mass difference. Wow. So each atom has its own stored reservoir of energy, which can be released if attacked properly. And this is what happens here. So so processes like that had been observed in chemistry earlier on by another famous Hungarian from exactly the same background. And yeah, that also inspired Szilard in some way. What's critical here is we need to have more than one neutron. Okay, if we have only one neutron, then the reaction will eventually die. You always have some additional losses. Some neutrons will fly out from your uranium mass. You must have more than one for it to be self-sustaining. And well, that was the tricky part, how to make sure there is enough. So that confirmation of uranium being an attractive chain reaction material really was finding out that on average it gives out more than one neutron. So that's 1939, and the war starts. Initially, it's kinetical energy of these particles. They hit other particles, everything eventually becomes heat. And a mass of uranium with chain reaction going on within a few millionths of a second can reach temperatures comparable with what's in the center of a star. That's exactly what it is. And then it propagates. It causes the world around it to receive that energy, and well, effects are...
Heat energy, right?
Eventually it converts to heat. Of course, there's also a lot of radiation, gamma radiation, and well, all sorts of energy releases, and full spectrum of radiation. So it's pretty severe. So the big question here was the mass. So the question of the critical mass was important, whether it's tons, and then it can't really be used as a weapon, or whether it's kilograms, and then obviously yes. Yeah, so most of that I already mentioned. Very quickly, nuclear programs were started in all countries involved in the global conflict. We had a Russian program, we had a Japanese program, we obviously had a German program as well. UK and USA initially worked separately and didn't share much information. So let me tell you a few words about these Japanese, German, and Russian programs first. The Japanese didn't really get very far. They had the basic concept right. They started some early processes leading to uranium enrichment and eventually construction of the bomb, but they were just lacking very, very simple resources such as high quality stainless steel tubes and stuff like that. In a country involved in a war, it becomes more and more difficult, and Japan had problems with that on many levels, so they didn't get too far. Germany lost its top physicists, and initially their program was moving on very, very well. However, they got one of the early measurements wrong, which kind of deflected their program into a direction, into a dead end, and they didn't really recover from that ever. So they were severely impeded by that. In Russia, well, it became very clear that the top nuclear physicists in the world stopped publishing, so Russians knew immediately that something is happening in the UK and in the US. There are some secret programs going on, which is when they started their own group. And, well, typically some physicists would alarm the authorities after independently realizing that the chain reaction is possible, to alarm them about that possibility, and then the government would in some way support the program or build a group or start a committee in charge of that. In the US, it actually was pretty difficult initially. So we had all these immigrants in US coming from Europe, and they couldn't get any attention to their claims. It only changed when Szilard went to Einstein, who was his old friend from Germany, and they wrote a letter to Roosevelt, which went for a number of major edits, and the letter was delivered through a personal friend of President Roosevelt to him. And this is how they got through the bureaucracy wall and got some limited support for early activity, which was really constructing a test nuclear reactor and making basic measurements, which would then answer the question, okay, how much uranium do we need for a bomb? Is it even feasible or is it not? There was a general confusion. The authorities didn't really know what to expect. There were three directions pursued in parallel: the bombs, the power for submarines, power source for submarines, and as a last priority, power generation for non-military use. So it wasn't clear to anyone at that time what's the most realistic goal to achieve on this time scale of several years, which is what they thought the war would last. Now, turns out that British scientists, or more exactly Italian and German immigrants in UK, doing their own independent research there with some support from the government, but they were still considered enemies in principle because of their nation. They really worked out the details. They realized that in uranium, the only way to turn it into a bomb is to rely on uranium-235. This is a particular isotope of uranium present in a very small, less than 1% concentration in the natural uranium. So they figured the only way to have a weapon of that mass scale, a few kilograms, is to enrich uranium, increase the content of uranium-235. And that information miraculously didn't go through to the US scientists for the next 3 years. The British and the Americans had an agreement. There was a deal between Churchill and Roosevelt to share information. They had committees in both countries, and the Brits would send that report with these numbers to the American committee a number of times, but the bureaucrat in charge of the American committee would not pass that further on. So nothing really happened in the US till 1942, and this is when they realized that the Brits already did all the work, and at least theoretically. And then they joined forces. The Manhattan Project was pushed full steam ahead. Between 39 and 42, it was in a very low activity period. From 42, it became one of the major war efforts in the US. And to show you the scale of that is, these are all labs which were built for Manhattan Project or which participated very significantly in the Manhattan Project. Some of them, well, most of them are still famous national labs in the US. We had 130,000 people working on that. And the cost in today's US dollars is close to 26 billion. So it's really enormous. It's, well, Niels Bohr said a few years before the war that the only way to, well, after discovery of the chain reaction, he said that the only way to make a bomb is to turn an entire country into a production facility. So this is exactly what the US did. And the main challenge was really getting the material for the bomb, I told you about uranium-245. It's only present in 0.7% in the natural metal. Enrichment is extremely difficult, mostly because the difference between uranium-235 and uranium-238, which is most of the natural metal, is so tiny. So it would have to be turned into gas, fluorium hexafluoride, which is extremely toxic and corrosive, and then through simple physical methods, repeated millions of times, it will be gradually enriched. It wasn't clear what's the best method, so 4 were pursued separately in parallel, and each of them would require amazing resources, efforts, construction of enormous plants, industrial plants, and none of them was perfect. So at the end of the day, all of them somehow participated to that initial stockpile of enriched uranium, which was used for the first bombs. So this is really where 90% of the Manhattan Project was. Although today, what people remember about is mostly Los Alamos and the actual construction of the bomb, because that's maybe a bit more interesting. People also realized that uranium-235 is not the only possibility. There was a major discovery that natural uranium, which is easy to get, and consists mostly of uranium-238, can, in certain conditions, absorb a neutron, and then it undergoes another nuclear reaction, and it becomes plutonium-239, which again is a valid fuel for nuclear fission. And the advantage it has over uranium is that it's produced in that clear, pure isotopic form, which can then be relatively easily separated chemically using chemical methods. The difficulty here is in production of that plutonium-239, not in its separation. And the production would happen in those early test reactors that scientists built for Manhattan Project, and would also be pretty laborious. So they were pursuing 4 different strategies for enrichment and an alternative fuel produced in another set of specially constructed facilities and then specially extracted. So scientists at Los Alamos designed the actual bombs. So here are just the cartoons showing the designs. The one on top is the uranium bomb. It's fairly simple. It's pretty much a gun. It shoots a bullet of enriched uranium into an enriched uranium target. There is a conventional explosive which powers that initial explosion. When these two masses join, the critical mass is exceeded. There is a little initiator somewhere there which produces the first few neutrons which start the chain reaction, and then instantaneously the explosion starts. So the bullet just barely touches the target and it all evaporates. With plutonium it wasn't that easy because it turned out that the plutonium had a fairly substantial intrinsic radioactivity. There would be just too many neutrons produced spontaneously in plutonium initially. So that scheme of a gun and a bullet would not work. The bomb would explode a little bit too early, and not entire energy would be converted into not entire plutonium would be converted into energy. The bomb would sort of explode, spread out lots of unburned plutonium fuel without causing significant damage. So that motivated this other design, which is at the bottom. It's essentially a ball of plutonium surrounded with conventional explosives. The thinking was the conventional explosion would uniformly squeeze that ball from all directions simultaneously, and although initially that ball would be under the critical mass, would not have enough power to explode, after this implosion it would reach the conditions to start the chain reaction. So that was very complicated, and the major challenge of the design and test at Los Alamos was really getting that configuration of conventional explosives around it right. And it was an extremely difficult task without computers. And the complication of that design really motivated them to have this bomb tested at the Trinity site near the lab. The uranium bomb was dropped at Hiroshima as it was, without any initial tests. People were pretty sure it would just work. With the plutonium, that certainty was missing. So just to start off the discussion, there is a number of motivations to really engage in the weapons development projects that scientists would talk about or try to explain themselves with. So certainly one of them is just curiosity in physics. And well, before the Trinity test, just a question of whether this would work was certainly a valid one. Another aspect of that is, well, scientists are to investigate the nature and find how things are, and if some of the truths discovered are dangerous or inconvenient, maybe world should deal with that, or maybe this will force the world or humanity to grow and learn to deal with those issues. Certainly, Robert Oppenheimer, the boss of the head of the Los Alamos lab, had a little bit of that approach. Initially, also, there was a real fear that Germans would get there first, and that building a bomb, maybe using that, would end the war, avoid further life loss. Curiously enough, it's exactly the same motivation that during the First World War was used to justify the use of chemical weapons. Some scientists, and really the greatest minds, had hopes for a future world with no wars, thanks to nuclear weapons. And my last slide will be about it. On the administration, military government side of things, pretty early the focus shifted from the Second World War to the post-war domination and superiority. So interestingly, Americans did not really put too many efforts into trying to find out where the German where the German atomic program was. They did invest a lot of effort to recovery of whatever was left of it after the war. But during the war, not much resources, not much intelligence was collected. There was not even no attempt to collect it. And the very fact of dropping the bombs on Hiroshima and Nagasaki was partly driven by short-term political goals, such as justifying to Congress this enormous expense, spending $26 billion on weapons which are never used. Well, that's really some thoughts for the discussion. Now, I mentioned Niels Bohr. He and a few other scientists, again Szilard and Einstein, really knew what was coming. They first realized that the nuclear bomb and later on hydrogen bomb, which was already worked on, are enough to totally destroy the planet. And Niels Bohr's hope was that the very fact that a weapon exists which ensures that both sides of the conflict are mutually and completely destructed would make wars obsolete. However, in order to use that death threat as a tool to ensure a lasting peace in the future, some means of control would have to be established. So he envisioned some kind of world government that would take control of nuclear weapons. However, the key part of that would be openness, and as opposed to keeping that secret and developing it privately, which inevitably leads to an arms race, which is exactly what happened. World leaders would have to sit down together, think about the possible consequences of a nuclear conflict, and then figure out that it makes no sense and just find a better way. Maybe he was naive. Maybe this is where the world got another 50 years later. It's hard to tell. Schiller and Einstein in particular, well, sent another letter to Roosevelt, again pleading to, first of all, not use the bombs in the war and focus efforts on avoiding the arms race. Bohr met personally with Churchill, who completely dismissed him, and once or twice with Roosevelt, again without much success. And yeah, the control of the process, technology, and invention was completely taken over from science to military at that time. And that's more or less where it is now. So maybe I'll just stop here. I went a bit over time, sorry about that.
Okay, thank you.